In this portion of the Solid Edge 2019 demonstration, we'll be looking at the flow and thermal CFD simulation capabilities within Solid Edge using FloEFD. The main target of our analysis is this subassembly, and if we open that up, we can get a feel for what's going on inside this particular model. We can see an enclosure with a PCB on which we'd like to perform a thermal analysis. First of all, let's have a look at the board itself. We can see a very detailed board 3D model here with all the components on the board modeled in intricate detail going as far as the pins in the connectors. This model may look physically realistic, but it's actually too detailed for an effective thermal analysis model. We need to create a more efficient thermal analysis assembly while maintaining accuracy. FloEFD has this capability under the EDA import option under the Flow Analysis ribbon toolbar. The FLOEDA Bridge is an optional module for FloEFD which allows for the import of very detailed PCBs into Solid Edge using the ODB++ file format. The ODB++ format is a neutral PCB format primarily used for manufacture, which includes information such as component size, position and height, along with copper geometry in the board such as pads, traces and vias. Most PCB layout tools can import this format. The information is imported and used to create a representative thermal model of the electronics subassembly. For example, a component can be picked and a power dissipation defined. If two resistor thermal data is present on a datasheet, this can be inputted here for the junction to board and junction to case thermal pathways. A tally of the power is kept and displayed. Alternatively, a thermal list can be imported to apply all the parameters in a single pass. A CSV file is used which includes powers, resistances and IC modeling levels. When this file is applied, the total power is updated and the components can be checked to ensure accuracy. Once the board has been prepared in the FloEDA Bridge, it can be transferred over to Solid Edge. The first thing to notice is that the chips are not modeled in such intricacy. This is fine as we are maintaining model accuracy while removing the mesh overhead that the detailed models induced. The FloEFD project is created automatically and the computational domain can be seen around the geometry. The project is set up for natural convection with the gravity vector shown on the screen. Materials are defined in the tree. The two resistor part is created and all the heat sources from the components can be seen labeled correctly. These can be clicked through to confirm power values. The PCB is defined according to the ODB++ stack-up data. The model has been pre-solved so we can review the results. A plot of temperature can be seen here with the distinct hotspot on the CPU. The model can be probed to get a feel for the temperatures at any given point. The unit system can be easily changed to move over to degrees Fahrenheit. Clicking on the CPU shows us the junction temperature of 164 degrees Fahrenheit. Spinning the board around shows the hotspot underneath at around 134 F. And all other points on the board as well. Airflow can also be visualized around the PCB. By animating the arrows, we can see the natural convection against gravity as the air is heated. Let's try a variant now by introducing a heatsink onto the CPU. Variants can be controlled using the Solid Edge alternate assemblies functionality. The simulation is cloned onto the alternate assembly and additional info such as heatsink material defined. A thermal contact resistance is also set between the heatsink and the CPU to replicate the thermal grease used. Loading the results, we can quickly see the difference this makes. There are no longer any red areas which indicate a lower temperature. There is also a change in the flow profile as more energy is transferred into the air around the heatsink. The larger surface area of the heatsink causes a slightly higher velocity than without a heatsink. FloEFD allows for results to be compared between projects. The exact same temperature plot can be extracted and compared side by side. The legend range is the same between projects for easy comparison. Let's move up to the sub-assembly model where the PCB will actually be operating. Here we can see the aluminum housing which has been made transparent. The board is inside, located on steel standoffs with the heatsink present. There is a motor and actuator mechanism and there are slots to allow airflow into the enclosure. There are also some slots on the rear for air outlet purposes. Two extra lid parts are present which close off the internal flow region and on which we can define boundary conditions. Using the FloEFD check geometry, we can visualize the air region within the enclosure. The blue volume is the air occupation region, and the complex shape can be seen around the vents and the electrical connectors. This part does not have to be created manually. FloEFD generates this automatically for an internal analysis. Looking at the general settings, we can see this is an internal case with heat conduction in solids enabled along with gravity, as indicated by the on-screen arrow. Environmental pressure boundary conditions are set on the lids, which take into account their respective elevations against gravity. The materials and FloEFD features from the PCB are applied at the enclosure level. Again, this model is pre-solved and we can look at the airflow in the enclosure. There is a lot of recirculation in the system and no real defined inlet to outlet flow. This is purely internal flow driven by buoyancy and temperature differences. If we show the flow coming from the top of the PCB, we can again see lots of internal recirculating flow, especially above the hot component. Some flow can be seen leaving the rear vent, as this is physically higher than the lower vent. The board temperature can again be visualized in the subassembly context. A maximum of around 190 F can be seen around the CPU, with the heatsink being red also. Let's again look at a variant analysis by introducing a fan to drive airflow. A solid edge alternate assembly configuration is defined with a small fan on the outlet. The aim is to exhaust the heated air and establish a forced convection current. The exact same simulation parameters are applied as before. Looking at the flow now, we can see a lot less internal recirculation. The flow is a lot more defined going from the lower vent to the rear vent. The exception is the front section where the velocity is much lower. By starting the flow on the heatsink, we can see the air being pulled from the vent, being heated and exhausted out the rear. The flow from the top face of the PCB shows a similar flow profile. Temperatures on the board have been reduced significantly compared to before. Comparing the results shows a noticeable difference in the colors. Numerically comparing the results shows that adding a fan reduced the CPU temperature by 23 degrees Fahrenheit. All the other components see a significant drop between 17 and 28 degrees F. Finally, let's look at the casing temperature. Here is the case with the fan. Some hotspots can be seen where the PCB screws down into the casing at around 75 F. If we compare it to the previous model without the fan, we can see the hotspots in the same place, but the temperature rises to 79 F. A cool spot can be seen at the front corner of the enclosure. It's very easy to compare and quantify different scenarios using FloEFD.